Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to talk about how to find the OH concentration and the pH of a weak base solution or a weak base solution. So basically this is very similar to finding the pH of a weak acid solution, but in this case we're going to be finding the OH minus or hydroxide concentration first. Make sure that the x is too small approximation is valid, and then use the equation where you have Kw is equal to the product of your H plus concentration multiplied by your OH concentration to find the H plus concentration. And then from there you could take the negative log to find the pH. So let's start with the first problem. Here we're given a 0.100 molar concentration of the weak base ammonia. If you're not given the balanced equation, then you got to write the balanced equation yourself. And again, all you're writing is the reaction of the base with water. So here you got your ammonia and you've got your water as reactants. The ammonia is going to take a hydrogen from water. That's going to leave the hydroxide ion, and then you're going to have ammonium ion for your product. So you're going to have your ice chart again. So we're going to do ice chart. We're going to do the initial concentration. So again, the initial concentration of your ammonia is 0.100 molar. And we're going to leave water out of it because water doesn't play a part in the equilibrium concentration expression or equilibrium constant expression or Kb expression for your base here. And there's so much of this that the concentration of the water doesn't change. So in general, we leave liquids and solids out of these expressions for that reason, that they don't change their concentration during the reaction. But these will. So we start out with practically 0 of each of these. The change, again, according to Le Chatelier's principle, the reaction is going to shift in this direction because we don't have any product. So that means we're going to lose a certain amount of our base, and we're going to gain the same amount of our hydroxide and our conjugate acid here, the ammonium. So plus X plus X. And again, that's because there's a 1-to-1 ratio in the equation. Now we add these together to get the equilibrium expressions. 0.100 minus X for here. And again, these are going to be plus X and plus X. And so now all we need to do is set up our Kb expression. So Kb for ammonia. So Kb is equal to, if we look that up, the Kb is going to be 1.76 times 10 to the negative 5. So 1.76 times 10 to the negative 5 is equal to concentration of the products over the reactant. So here we're going to have OH minus concentration multiplied by NH4 plus concentration over the concentration of NH3. And so now we're going to plug in our expressions here. So we get 1.76 times 10 to the negative 5 is equal to, these two are both x, so multiplied, it's going to be x squared. And then we have our 0.100 minus x. Now what we can do again is we can do the x is too small approximation. And so you can see here that this is the initial concentration is 0.1, which is 1.00 times 10 to the negative 1. Here we have 10 to the negative 5. That's a difference of like a factor of 4, the power of 4. So it's about a 10,000 factor difference. So that's probably going to be a valid assumption or approximation. So we'll get rid of that. Now what we need to do is multiply both sides by 0.1. Then take the square root of both sides to get x. And when we do that, we get x is equal to, let's see, 1.33 times negative 3. 1.33 times 10 to the negative 3. So this is x. X is our hydroxide concentration, so we've got our hydroxide concentration. But if we double check our approximation, our x is too small approximation, we need to check the ionization percent, or whether or not this falls under the 5% rule. So if we take the 1.33 times 10 to the negative 3 divided by the original concentration, 0.100, multiplied by 100, we get a percent of 1.33. So the percentage is less than 5. So this is a good approximation. So the x is too small approximation is valid. So we can keep x as 1.33 times 10 to the negative 3 for the OH concentration. Now we need to find the H plus or hydronium ion concentration. So here we can take this. So remember, Kw is equal to 1.0 times 10 to the negative 14 is equal to the hydronium ion concentration plus, or multiplied by the hydroxide ion concentration. We know the OH concentration is 1.33 times 10 to the negative 3 molar. And so when we solve this, we get H3O plus concentration is equal to 7.52 7.52 times 10 to the negative 12 molar. Let me double check to make sure I got that right. Yeah. And so now that I have the H plus concentration, or the hydronium concentration, all I need to do is take the negative log of that number. If I take the negative log of that number, then what I get is 11.124. So the pH is equal to 11.124. Let me double check. Yep. Now notice here again, with regard to significant figures, notice I have 3 sig figs in here. The rule again is when you take the log of something, whether it's negative or whatever, if you take the log of a number, then the rule is whatever number of sig figs you have in the number you're taking the log of, then your answer should have that number of decimal places. So the significant figures, the number of significant figures translates into the number of decimal places. So you'll notice I have 3 sig figs here, and I have 3 decimal places there. So that's how you keep track of your significant figures. Okay, so that's the first one. Let's go ahead and do the second one. So again, the second one is going to be the same. You're going to have your ice chart. We starting with this concentration. So here we're going to have 0.33 molar, and we're going to ignore water, and this is going to be practically 0, as well as this. So we're at 0 initially. We're going to go this way according to Le Chatelier's principle. So that means we're going to lose a certain amount of our base, and we're going to gain the same amount in our hydroxide as well as the conjugate acid of the base. Okay, so now that we have this, we have our change. We add these together to get the equilibrium expression, 0.33 molar minus X. So this will be minus X. And this will again be plus X plus X. We set up our KB expression. The KB for this is, what's the KB? The KB for methylamine is 4.4 times 10 to the negative 4. So we have 4.4 times 10 to the negative 4. That's going to be equal to the concentrations of these. So concentration of the products, CH3 NH3 plus, over the concentration of our base, which was CH3 NH2. Okay, now we plug in the expressions. So that's going to be 4.4 times 10 to the negative 4 is equal to x squared over 0.33 minus x. Again, we're going to do the x is too small approximation, so that will be negligible. So we'll get rid of that. Solve for x. So multiply both sides by 0.33. Square root both sides to get x. And when we do that, we get x is equal to, okay, we get 1.204 times 10 to the 2. So 2.0, let me check that again, 1.204. So that's 1.204 times 10 to the negative 2. So again, this x value is our OH minus concentration, but we need to check our percentage here. So check our validity of the x is too small approximation. So 1.204 times 10 to the negative 2 divided by our original 0.33 times 100 is going to give you 3.65%. So we get 3.65%. So the x is too small approximation is valid. So we can go ahead with our x. So here we have x. That's going to be our OH concentration. What we need to do is then go back here and use that equation again. So here I'll erase this. And so we get KW is 1.0 times 10 to the negative 14. That's going to be equal to the OH concentration, H3O plus concentration multiplied by the OH concentration, which is this. So 1.204 times 10 to the negative 2. And then when we solve this for H3O plus concentration, we get 8.305. 8.305 times 10 to the negative 13 molar. And then when we take the negative log of that, we get 1.21. So then the pH, I'll write here. The pH is equal to 1.21. Oops. 12. That's going to be 12 point. That's going to be 12.08 for the pH.